Welcome to another lesson of the course Curves in Engineering and Architecture. We are in the second part of the course, namely Curves in Road Safety. In Module 5, we speak about three mathematical concepts that serve to solve a problem in road safety. Lesson 5.2 is about integration as a tool for getting parametric equation of transition curves. Remember that in Module 4, we wanted to design comfortable and safe roads, and we focused on horizontal alignments. We then looked for transition curves whose tangent direction varies smoothly. As curvature is the size of change rate of tangent direction, the clothed curve solves our problem because at each of its points the curvature is proportional to arc length, and therefore the radius of curvature is inversely proportional to arc length. To lay out a clothed in the field, we want parametric equations giving the coordinates of each of its points as functions of the parameter arc length. In Lesson 5.1, we got a differential equation giving us info about the derivative of the angle function with respect to arc length, and now in this Lesson 5.2 we're going to find the corresponding function solving this differential equation through a process called integration. After that, in Lesson 5.3, we will recover from the angle function the position of points of a clothed by using integration again and also polynomial approximation. We recall in Lesson 5.1 that the derivative of the function space with respect to the variable time at a given instant, in other words, the instantaneous velocity at that time, is the slope of the tangent line to the graph of space versus time at the corresponding point, and this slope can be computed as the limit of slopes of secant line to this graph when the size of interval time tends to 0. In this way, derivation is a process that takes as input a function f of x and gives as output another function f prime of x, assigning to each number a the derivative of f at this a. For example, the derivative of a space function with respect to time is the velocity function depending on time too. Now, to solve an ordinary differential equation, we want to define the inverse process, called integration. This process takes as input a derivative, for example, the velocity function in a given interval of time, and gives as output the space traveled along this time, that is, the variation of function space in the given interval. This is easy to compute when velocity is constant, as traveled space is the product of the constant velocity by the time elapsed. We call this quantity the definite integral of the velocity function over the interval of the variable time. Graphically, this is just the area of the rectangle given by the graph of the function velocity in the given interval of time. But what happens if velocity is not constant? Analogously, the definite integral of the velocity function over the given interval of time is the area determined by the graph of the velocity function and the horizontal axis. This number gives us the space traveled during the interval of time considered. In general, the definite integral of a non-negative function over a given interval of time is the area determined by the graph of the function and the horizontal axis over the given interval. To determine this area, we approximate the region considered by a collection of rectangles below and above, so the area is always between the two sum of areas of rectangles considered. Now, if when the number of these rectangles is infinitely big, these two sums are infinitely close to the same number, then this number must be the area we were looking for, and the given function is called integrable at the given interval. Besides of this mathematical idea to define this area that can be rigorously formalized as a limit, we wish to effectively compute these areas. For that, we think about the easy case when the velocity function was constant and the area was that of a rectangle, representing the total variation of a space function during the time elapsed. In this case, the space function was the antiderivative or primitive of velocity function. In general, a theorem can be proved the fundamental theorem of calculus, in fact saying that, as in the easy case, the area determined by a non-negative integrable function small g over a given interval is equal to the total variation of an antiderivative of the given function in the interval considered. Looking again at the simplest case, that of a constant function, it is clear that the definite integral between 0 and every number t of the constant 1 is equal precisely to the number t. So we say that the indefinite integral of the function g of x equal to 1 is the function big G of x equal to x plus any constant, say c, because constants have zero derivative. The mantra is, as the derivative of x is 1, the integral of 1 is x plus a constant, and the idea behind is that integration is inverse to derivation as processes acting on functions. You can practice this with your favorite couples of functions. For example, as the derivative of sinus of x is the cosinus of x, the integral of cosinus is sinus plus a constant. To derivate a function, you have rules based on the definition of derivative we saw in lesson 5.1 that you can always systematically apply, so derivation is an easy process that you can always do, but integration is not easy in general. To integrate a function, small g, the key is to find a function whose derivative is precisely the given function small g. If you have obtained small g derivating a function big G, as in the previous example, the integral is immediate, but if not, you may have to apply a collection of methods to discover who is big G. In fact, for some functions, as the exponential of x squared, there is no way to express its integral as a known function, that is, as a combination of elementary functions as polynomials, trigonometrical, exponential, etc. These integrals constitute new functions in themselves. For example, the integral of sinus and cosinus of a variable squared are the so-called Fresnel integrals, as we will show in action later in this module. But let's come back to our goal of solving the differential equation given by the curvature property of a clothoid that makes it useful as transition curve. First, we separate variables angle and arc length, expressing our differential equation as derivative of the angle equal to arc length by the constant 1 over a squared times the derivative of the arc length. Now we integrate with respect to our length s, so the angle function phi of s will be equal to 1 over a squared times the integral of s, which we know is s squared over 2 plus a constant. This gives us a different solution for every number c, so we got a whole family of solutions, which is the typical situation when solving a differential equation. The question is, can we select from this infinite family of solutions the one we are looking for? Remembering that we know that initially when the arc length traveled is 0, the angle phi is 0 as well, we will find that phi of 0 must be 0, so the constant c must be 0 too. A differential equation plus an initial condition of this type is known as an initial value problem that typically has unique solution. So in this lesson we use integration as a mathematical tool to get the angle in terms of arc length for every point of a clothoid. Geometrically, we have found the tangent vector to the clothoid at each of its points. That is the vector given by the derivative of coordinate function. From this derivative in lesson 5.3, we will use polynomial approximation and integration to finally get the parametric equations of a clothoid.